Yes, so now we come to some pleasant part of the story. Maybe I'll turn this on. In the sense that we will actually solve some non-trivial enumerative problems using the tools that we had. So the tools so far, I just introduced a general framework of Chow groups, calculations, intersection numbers, and then we had some little tools. So one was just direct intersections, and that was this Schubert calculus in a sense that Simone explained last time. But we are not going to carry that to the end because that's not my favorite thing to do. Then we introduced Chern classes and the calculus of Chern classes, and today it's going to be about that. And using that, we're going to solve some non-trivial problems. So first, I'll just remind you a little bit of, where am I? Of what was going on. So just start somewhere. So let's just discuss the Chow group or cohomology group of the Grassmannian. So let's just since we haven't seen each other for 2 weeks, so I just start somewhere. So Chow ring, or the same thing, cohomology ring of the Grassmannian, I denote it this way, right? So this space is just the, right, is just the set of, so I'll use the notation of the book, capital lambda for the subspace now, lambda in a n subspace of rank k, right? So this is a beautiful projective variety. And so what Simone discussed last time is that this actually falls under this wonderful simplification that only exists since 2014, the work of Totaro. It has an affine stratification. So this Gruppe N has an affine stratification. Right, and it's the following. It's we define the strata. Now, so I'll define maybe the closed strata. So so I take the following data. I use mostly the notation of the text. So I take this number n minus k, and I take a sequence of numbers, of k numbers, k non-negative integers. And I'll denote this by A. These are integers. Well, I'll put a bar on it just so that it's a vector, okay? So maybe it's a bit better. Okay, I look at these numbers, and to this we associated a sigma A bar, okay? This is some closure of a cell. So if I take the open part, I take away everything, then it's an affine cell. So let me just remind you, maybe in my language, how it works. Actually, it's a nice diagrammatic way of looking at this. I'm sure Simone showed this also, but maybe slightly different notation. So that is the following. So how I define this sigma A bar, I'm explaining. So you do the following. You fix a flag. So the flag is just V1, V2, n, and Vn is of course just the whole space. So this is a flag. Of course, the rank of Vi is just I. And so you just fix a flag, and we are going to define this story regarding relative to this flag. And the idea is approximately the following, not approximately, precisely the following. So you actually draw. You draw a rectangle. You draw an n minus k by k rectangle. So here is n minus k, the height, and here is k. And so a good way of doing it is the following. You can write here maybe Vn, and then you go on and you go, so this is k, so this is just going to be Vn minus k plus 1. right? If I, maybe I will just do slightly wider one, okay, so maybe. So this is Vn, and then I do a little table like this. Like that. And so the first one here is just going to be Vn minus k plus 1. So the next one is just going to be, and then I go up, so this goes down like this, and it also goes down in this direction, okay, the indices. So it's just going to be Vn minus 1. Here is going to be Vn minus k. That's n minus k. And so then if you go all the way up, say n minus k, so then it ends up at V1. And then you have V0, which is just 0. It's nothing. So, right? And then here you go all the way down, and that's going to be, so this k of them, so that's going to be Vk. Right? So this is the 4 corners of the rectangle from V1 up to Vk, and from Vn minus 1 to Vn minus k to Vn minus 1. Okay? And so otherwise, the index, you put those spaces there. And now, you draw the Young diagram, so you draw a diagram with A1, A2, AK. This is the A axis, if you like. And so here is A1. And then next is going to be A2. And some of them could coincide. Of course, it's A2. This is A3. So this is the height of these things. And then what this tells you, what this diagram will tell you is so a priori, if you look at a random lambda, now we look at a random lambda, and of course what we are trying to understand is what are we are studying the intersections, the dimension of the intersection with some of these VIs. This is what we're looking at. And so what this table tells you is that in the ith column, you're looking at which is the smallest v which still intersects lambda along that many dimensional, well, when this dimension is that. So more precisely, so we are looking for this condition, or greater than equal, and we are looking for the minimal j, which satisfies this condition, okay? And that's what's shown here. It's this top element here. This is this, so this is this ith column here, and here you see v, this is the minimal j, satisfying this condition. Okay, so again, you draw the diagram with the v's, it's fixed, then you draw the Young diagram in it, then you look at the top element in the Young diagram, the top v index that you see there, and that's going to be the minimal j for which this is true in the ith column. Now, of course, the thing is, I can also write it down with the formula, but the formula is so many indices, it's a little confusing. That's the problem. That's why I was trying to explain in a more clear fashion. So the formula is just this. It's just that the dimension, so it's the lambdas for which the rank or the dimension is the same thing. Well, let's call rank here, okay? The rank of the intersection of lambda and, but then you have to shift the indices. So let me just, so this is lambda, the lambda element. So the rank of, and then you have lambda intersecting with v, and then something like n minus k plus I minus ai, something like that. This rank should be greater than or equal to I. So to me, this is a little confusing. But precisely if you translate this condition, then this is what you get. That the minimal j for which this condition is true is the top element in the ith column that you draw here. Okay. Well, let's just see quickly our standard example. So, for example, so this is the minimal j here in the ith column. So the ith column corresponds to ai, of course, right? Because it goes. So if we So I'm sure you've seen this. So we look at the case, so k equals 2, n equals 4. And then you see this square. So then you have, so we have, our square looks like now V3, V2, V2, and V1. This is what it looks like now, the square, the thing I drew. And then we have the cases, well, the sort of 4 interesting cases. So this is one. So this is when this corresponds to A1 equals 1, right? So I'm drawing the diagram now. So it's A1 equals 1 and A2 equals 0. So I'm not going to write that out, but that's what this means, right? So I'm just, this is height A1. So just an example, A1 is 1. That's the height of the first column. And A2 is 0. That's height of the second column. Okay? So this, I have no space for that. So then the next one is, you can have this one, and then you can have this one. These are the most interesting ones, right? So one important observation here was that the codimension, so note the codimension of sigma A is equal to just the sum of the AIs. So here the codimension is 1, here the codimension is 2 and 2. And here let's explicitly write down what we see. So there's one little remark. You will see it's a little simpler. I mean, for example, this looks like you have a condition for every I somehow, but it's a little simpler than that. So here, the point is that when you have 0, that actually is no condition. It's easy to check. So actually the only condition here is that V2 intersects lambda in a non-trivial way in this 4-dimensional case. So it just means that the rank of V2 intersecting lambda is equal to, is at least 1. This is the condition for this thing, right? That's the first one. The second, so the one point is that when you see a 0, that's no condition. And the second is that if you have these even things, that this one actually implies this. I mean, that's because, I mean, you already see that it's a decreasing thing. That's for a reason. So the second one is implied for us. So here you just take this condition, which now says that the intersection of V3 and lambda is at least 2. So you see that actually here lambda is in V3. And here it's that thing, but now the intersection of V1 with V2 with lambda should be at least rank 1, and so that just translates into V1 is in lambda. Okay, so I'm sure you saw this, but maybe slightly different pictures. Okay, so it's clear? So these are the interesting things in our stratification. Okay, so this, now you can check that there is altogether 6 possible diagrams. I wrote down the 3 interesting ones, but there is 3 less interesting ones. And satisfying that, and that corresponds to the 6-dimensional cohomology or whatever Chow groups that we had. Okay, so this is was our first basic point of view. So now I'm going to go to the language that I prefer, and that's going to be the language of Chern classes. So probably you've seen this as well, but maybe didn't develop this part. So Chern classes. So I remind you what the basic setup was that interests us, and this is that we have the Grassmannian, we have the tautological subbundle. So more precisely, I have this tautological sequence. So yeah, there's always some annoying thing with writing it down. What did I decide? So yeah, so the subbundle, first I write it down. So this S, we remember, is just defined this way. it's a pair of a lambda and V in the Grassmannian cross AN, and such that this is the incidence, right? The V is in lambda, right? This was our tautological subbundle. And subbundle the following sense that I can look at this trivial bundle, so gr times AN, and this is the subbundle, right? So, and this, so now this is the annoying thing that, actually it's the other side, I think, AN. So there is a sequence of vector bundles, exact sequence of vector bundles, where this S is the subbundle of this, and this is the quotient bundle. This AN is a somewhat of a loose notation because, in fact, it should be this product, should be the bundle, and not this, but we think of it this way. So I hope this is clear. So this is now rank K, and this is rank N minus K. Okay? All right, so we can, we know that these are bundles, so we can write down their Chern classes, write down the Chern classes, and we introduce a calculus using, and the only thing we're going to be using is Whitney's formula. So the calculus of these Chern classes, let's introduce them. So for S, for example, C of S, let's call it, say, 1. So these are first Chern class, second Chern class, plus the kth Chern class. It's a rank K bundle. It has K Chern classes. And let's go with Q also. So you'll have CQ is first Chern class. Well, now I have to use another letter, so I'll use S. S1, S2, plus, and of course we know it's an N minus K dimensional rank bundle, so it should have only, but I'll pretend that I'm stupid and I'll introduce actually all of the Chern classes, okay? As if I didn't know that Sn minus K plus 1 is 0. Okay, so we have this one. And so now, let's write down the last Chern. What is the Chern class of this trivial bundle? So I'll denote it this way. I'll put this bar left or right. It doesn't mean anything. So what is this Chern class? It's trivial bundle, so it's 1, right? Okay, and then what does Whitney say? Whitney tells us that the product of these two is product of this thing and this thing in this. So Whitney tells us that CS times CQ is equal to 1. And this is a remarkable equation because if you look at it, you very quickly discover that actually, so it's a little lemma, is that Whitney's equation, so this equation, Whitney implies a simple polynomial expression, of SL in terms of in C1 up to CK. So actually I will maybe somewhat, well, let's do it anyway. We'll just go here. So let's write them down. They are very simple because you see you have, well, you take the grading into consideration, then it's clear. You know, you just take this product and you express, for example, C1 of, which is 0, of AN as this product, and you calculate C1. So what you see is that if you calculate C1 of AN, then this gives you, this is 0, of course. This gives you the following relation. It gives you that C1 plus S1 is 0. That's your first relation, right? The next one, C2 of AN. Again, now think of AN, I'm sorry, this is really a loose notation. It's not the C2 of the vector space, it's of a trivial vector bundle over the Grassmannian with fiber AN, okay? So then we get, well, we get S2, well, we can try anywhere. Anyway, let's try the way it was. Anyway, C2 plus C1 S1 plus S2 is 0, etc. So you see the general formula will be like this, is that SL, so you will get the CL of AN will just give you the following formula. SL plus sum of CI SL minus I is 0, where I goes from, so now it goes from 1 to L minus 1. Right. 1, yeah, and L minus 1 is 1. Oh no, to L, sorry. L, then this is what I'm confusing. Yeah, L, and I would try to say we define as 0 to be 1. Yeah. Okay, that's what I wanted to say. Okay. All right? So it's the lemma is so this formula's lemma is implied because you see that in every expression, SL is a monic polynomial on these things, and on the other hand, inductively, since if you already know as the smaller s's, then I can express them this way. Okay, so let's actually do this for our case. So let's what this looks like in the case. So k equals 2, n equals 4. So what do we get? So what we get is the following. We have C1, so we get that S1 is equal to minus C1. That's the first equation. The second equation says that S2 is equal to, so now this is minus C1, so it's just equal to S1 squared. And I'll peek a little bit because then it will be, I won't make any mistakes. Now it's easy, but S1 squared minus C2. And then we go S3. And S3 is going to be equal to, so we use the next one. So what do we have? We have, so the point is that here, let's simplify a little bit because we do not have C3. C3 is 0. So this will not fully contribute. So they'll, instead of 4 terms, we only have 3 terms. So S3 will have expression only in terms of 2 things. And so it will be just, now where am I? I'm here. So it's minus C2S1 minus C1S2. That's what we get. And so when we express this, then we just get C1, C2 plus another time C1, C2 minus C1 cubed, right? So the first comes from the first one, because minus C2 S1 is just C1, C2. And the second one, when I multiply S2 with this, I get this term. So you see, I get just 2 C1, C2 equal C1, C2 minus C1 cubed, okay? Okay, and so as I said, I remember I said I will pretend that I'm stupid, and this is the time when I will undo this. So we are not stupid, and of course we know that the rank of Q, so remember that C3, okay, so recall that S3 is just C3 of the bundle Q, and this is 0 since the rank of Q is 2, right? Since it's n minus k dimensional. So it cannot have a Chern class. So this actually is 0. So what you see is that not only what our lemma just said, that this thing is an expression, that the S's can be expressed, but amazingly, actually, you get relations also. Not only the S's can be expressed, but you also get relations in the C's. So this leads to the following relation. And this relation just says that 2C1, C2 is equal to C1 cubed. Okay? And so now let's do the next one. This is S4. But now I'm going to use this relation that I already know that S3 is 0, so that I don't need that. So that also gives me, just eliminates terms. So we don't have C4 is 0, so remember that. We know that C4, C3 is 0, C4 is 0, and S3 is also 0. So when I do that expression, this expression becomes much simpler because the only terms I have is just basically the same two terms. So if you do that, then you get the term here. So S4, you'll have C2 times S2. So you just multiply C2 times S2, you multiply that here. And then you get just C2 square minus C1 square C2. This is what you get. And everything else will be 0, actually, because there's no other things. Because if you have every other term will have something that has a 3 in it. And a C3, S3, etc., they're all zeros. So the only thing that can be here is just S2 and C2. And so that's the only thing you get. But, of course, we know, again, that this also has to be 0 because Q has rank 2. And this is the fourth Chern class of a rank 2 bundle that also has to be 0. Is also a relation by a 0 leads to a relation, which tells me that C2 squared is equal to C1 squared C2. Okay? And now it's an easy exercise to verify that these relations describe a ring precisely of the correct dimension. So let's write down the actual, and so now, well, I'll erase this, but I sort of exactly want to compare it to this, but I mean, you know this. You'll have it. So what we see, what we see is that, so what is it? So let's consider now the following ring. So let's look at the ring generated. Actually, I'll look it over the integers by just these two monomials, C1 and C2, which, using which we can express everything. And then we just divide by the following relations. So one relation says that C2 squared is equal to C1 squared C2. That's the S4 case. And the other was that C1, 2C1, C2 is equal to C1 cubed. Okay? And so you can see that, whereas it's pretty clear, so it's an exercise that you get precisely you can write down a basis so that this ring, the dimension of this ring is 6, and in the graded version so by graded I mean because this has degree 1 and this has degree 2, so then I have degrees 0, 1, 2, 3, 4. Here we have 1 that just gives, so this is degree. So that's just 1, just given by the element 1 of this ring. This is just also, this is the dimension, and this is sort of the basis. So here the basis is 1, here the dimension is 1, is just given by C1. And now here the dimension is 2, given by C1 squared and C2. Those two things. And then for 3 already, you'll see that there's, because we eliminated everything else, everything can be expressed via C1 times C2. And here everything can be expressed via C2 squared. Okay, so you can just check that these relations give you this actual basis of this finite dimensional ring. So this is just the amazing thing you can think of is an ordinary, we can go back to an ordinary polynomial ring. It's a polynomial ring in 2 variables and 2 relations, and it's just supported, I mean, it's a scheme, actually, in our language. Okay? It's a scheme, actually, the scheme is sort of a complete intersection. It has 2 relations and 2 variables. Okay? And the cohomology of the Grassmannian is actually a scheme, a complete intersection scheme. That will be the theorem I will tell you. But I wanted to point out one thing before that, and that's that this actually, amazingly, it seems like I haven't done anything, amazingly actually gives the answer to our question about the number of lines. Well, we already done this, but what I did now gives you the answer to the number of lines intersecting 4 fixed lines in so one remark. This answers our problem, the number of lines intersecting 4 given lines in 3 space. Well, in P3, say. Okay, so why is that? Because you remember that we expressed this since C1 is precisely, I just had that up there, is the space of lines intersecting one line, a given line. So this, I'm not going to explain this again, but you can check, we've done this several times, that this is just equal to the degree of C1 that's intersecting a line, and then you have to take the 4th power for the 4 given lines. Okay? This is what we're trying to calculate, and what this tells you here, if you are careful, it's this relation actually. Oh no, this is not correct actually what I wrote here. No, it is correct, yeah, C2. Yeah. So if you check this, you can easily see, for example, why you have a 1 here, is that C2 squared is equal to C1 squared C2 is equal to, and C1 squared C2 is equal to, I multiply this by C1, I get 2 C1 squared C2, right? So it's, what I'm trying to say. Yeah, okay, so, well, let's put a 2 here, just so that, yeah. So let's just say 2 C2 squared is equal to 2 C1 square C2, but 2 C1 C2 is C1 cubed, so this is equal to 2 C1 to the 4th. This is the relation we get. That 2 C1 to the 4th is this, just C1 to the 4th, sorry. Yeah. C1 to the 4th, right? So 2 C1 squared C2 is C1 to the 4th. So we see that the degree of C1 to the 4th is the same. So this calculation shows that this degree is the same as the degree of 2 C2 squared. But if you remember what C2 squared was just the intersection of 2 planes so C2 was the space of 2 planes contained in a 3-dimensional space. That was and C2 squared, that means that you calculate, so C2 squared, okay, I write this down, is the number of 2 planes contained in two generic 3-dimensional, rank 3 subspaces. And of course, that's 1. I mean, if you take 2 in 4-dimensional space, you take a 3-dimensional space and another 3-dimensional subspace, they intersect in a 2-dimensional subspace, and there's a single 2-dimensional subspace contained in that 2-dimensional subspace. Okay, so C2 squared is just the enumerative question that you take 2 planes. Sorry, it's 2 planes, not 2 planes. It's 2 planes. It's 2-dimensional planes. So you're in 4 space, you take 2 generic 3-dimensional subspaces, and you're counting the 2-dimensional planes containing them. That's obviously equal to 1. Okay, so C2 squared is 1, and this degree of 2C2 squared is equal to, so it's equal to 2. So degree of C2 squared is 1, degree of 2C2 squared is 2, so this thing is equal to 2. So we prove that there's 2 lines. This is pretty crazy. Yeah. Okay. So again, this calculation, this mumbo jumbo with the relations and just a little thing about interpreting Chern classes actually gives you that answer. Okay. And so then I just want to make a few, so maybe I'll now want to make a few remarks now before I stop. So the first remark is that this theorem actually is true. I'm not going to prove it. It's a little technical. It's not, as you can see, it's just some algebraic mumbo jumbo. It's not so difficult. I mean, so theorem. So somewhat again loosely, so following the lemma, consider SL as a polynomial in C1 up to CK in our general setup, right? So as the lemma says that every SL is a polynomial in C1 up to CK, right? So this is what I proved this there. Then, quite obviously, if I take any polynomial in these things, and any polynomial here defines an element of the Chow ring, right? Because Ci is so I have a map from here to the Chow ring, and what we also saw is that I can define, I can find relations in this Chow ring and where the relations start, where they precisely start above the rank of Q, so they will start at S. So remember, the rank of Q was n minus k, so it will start 1 above. Sn minus k plus 1 will be 0, like here S3 was 0, right? And then S4 is 0. So we start here, Sn minus k plus 1. Etc. And I need to take as many k pieces, so the last one it will be precisely Sn. So I take a polynomial ring, well, I can take it over Z, it turns out, and I just did precisely what I did here. And I take the relations Sn minus k plus 1, that's here, all the way up to Sn. And I divide, I get a quotient ring, and the claim is, obviously, this thing now clearly has a map onto the Chow ring of the Grassmannian. Right? Because this is obvious because these are elements of the Chow ring of the Grassmannian given by those linear blah blah, the way we define the CIs, and I just take products and that's defined. And it's obvious, and I explained it, that these are actually relations, so that's also true. So this is definitely a map, and so the statement is that this is an isomorphism, so this actually is this is an isomorphism. And I would like to point out one thing is that, well, you can see that one algorithmic way of the computer, you can prove this easily, because what you do, you give the computer this ring and these relations, the computer calculates the ring, and then you calculate the dimension of the ring, and then you can see, this is more or less a proof, that those dimensions correspond to the dimensions coming from the stratification from the Schubert classes that we had, that we know are a basis of the Chow ring. Because remember, because we have as affine stratification, we actually have an actual basis of the Chow ring, so we know precisely what dimensions they are. So we can compare the two, and it works. It actually works. But I would like to point out that the things we get this way are rather different. It's not the same flavor. For example, I said there's a basis, but actually this basis is not so clear, not so well defined, because it's just a polynomial ring divided by some relations. So I might have chosen some different classes here. So the basis in this thing is not so well defined. It's not clear. We have generators of the ring, but the basis is not so clear. Also in this setup, it's completely clear that the the Chow ring as a ring is generated by k elements. In the Schubert class, when I just defined that, that's not clear that as a ring how it's generated. So this is perpendicular points of view, very different, gives you a very different flavor. Okay, and that was one thing. And then another thing, I still have a little time, I wanted to explain. Maybe I'll just do it here. Just an amusing fact that if you use the splitting principle, then you get some, this is it will be an exercise for you. So, well, first, just maybe before even that, I can, the relation between these S's and this, and between these classes and the Schubert classes, so, or what do we call them, Schubert classes, the sigma A? Yeah? Okay, so this, so note, so one statement is that Ci is just actually equal to sigma, so this was the class of that A things. And for here, A equals to 1, 1, etc. 1, maybe there is a minus 1 to the I, the way I defined it. And here, this is I times. While S L is just equal to sigma L. So, and then 0, 0, 0, 0, 0. Okay, so this is, so actually these S's and C's are closely related to the classes, but once you start multiplying them, you see you lose. So once you use the ring structure, you kind of lose sight of what's going on. But the classes themselves fit very well into the Schubert class story. It's just that. So that's one thing. So these are going to be exercises. The other thing which are kind of amusing, and this is what I want to show, is that using the splitting principle, we have a kind of a funny interpretation of what's going on. So because what does the splitting principle tell us? It tells us that we can introduce some classes, which are the Chern classes of some line bundles somewhere, but it doesn't matter for us now, which says that basically just formula-wise, it just means the following, that if I take one C of S, which is just equal to 1 plus C1 plus etc. plus CK, that this can be factored into a product of 1 plus some, well, abstract classes xi. You can think of them this way. Right? So this is what the splitting principle looks like. It factors the Chern classes into products of just linear terms, and then we think of these ones as in this case, then the Ci are the what's called the elementary symmetric polynomials. So do you know the theorem about symmetric polynomials, that they are generated by elementary symmetric polynomials? Yeah? So there's a theorem that says that any symmetric polynomials actually can be written in terms of these elementary symmetric polynomials in a unique way. Okay? So the amusing thing is, I can ask you, okay, and what are the S polynomials now? So what are these polynomials in terms of these? Because now, you see we have expressions. I said that you can express all the S's using the C's. So that means this is some kind of elementary symmetric polynomial, these S. So what are they? Okay? And so the other exercise is to say that SL is what's called the totally symmetric polynomial. I think it's called totally or something like this. But in any case, it's the following. SL is just equals to sum of product. Well, so it's just X lambda. Well, lambda is L. So I don't know how to, well, I just don't want to introduce so much notation. But what I mean is just, I'll finish with this. Is just the sum, this is just the sum of all monomials of degree L. So for example, let me just show you quickly what I mean here. So for example, here, S2, let's do this formula here. So S2 is equal to C1 squared minus C2, right? Well, this is now the elementary symmetric polynomial. So this is x1 plus x2. That's the first elementary symmetric polynomial. I'll square this. Minus the second. That's x1 times x2, right? And this is just x1 squared plus x1 x2 plus x2 squared. See, so this is all the monomials of degree 2 with coefficient 1 just listed. That's what they are. Okay, so that's another exercise which we'll use later. Okay. Okay, so let's take the break. I can have my cookie. Okay. So what else? Yeah, maybe just one last amusing thing, which actually then generalizes, to finish this remark, to what's called Borel's theorem for the general for the cohomology of any homogeneous variety. You have an expression like this. So I can just rewrite now this thing in this other language, and it gives you this amusing fact. You can write now that the cohomology of the Grassmann, let's write it, Kn, the Chow and the cohomology is the same thing of the Grassmann, and can be expressed in the following fashion. So instead of this now, I write everything in terms of the x variables, since they are the same, but now the polynomials are symmetric. So I can write it in the following way. It's z x1 x k. But now I only take symmetric polynomials, so it's sk. So I divide by the symmetric group. So I only consider symmetric polynomials such as x1 plus x2 or x1 times x2 and things generated by it. And I divide this now by relations, and the relations are these totally symmetric polynomials. So you can write here, so it starts with Sn minus k plus 1, which is a concrete symmetric polynomial. So that just starts with, say, x1 to the n minus k plus 1 plus, I don't know, x1 n minus k times x2, etc., etc. You take all monomials whose total degree is n minus k plus 1, and you add them up. And then you do the same with s, etc., all the way until Sn. And you can write them out again. So you get, so it's a little hard to see precisely what's happening, but that's the formula. So maybe for this case, we can even write it out now completely for just the case 2,4, so that you see what I mean. Is that for example, a gr 2,4 is just, you look at the symmetric polynomials in two variables. So you divide this by just, well, you know what symmetric polynomials are in two variables. And then you just divide by an ideal generated by two polynomials, and you can write them out explicitly. One of them is x1 cubed plus x1 square x2 plus x1 x2 squared plus x2 cubed. And the other relation is the same thing with x1 to the 4th. Okay? And this quotient is the cohomology ring. And this is true, it turns out, then you can much more generally, or any partial flag variety, or even for more general Lie groups, I mean, they're the exact same analog is to, and this is called Borel's theorem. Okay? So I want to say this, and maybe And before I go to this enumerative application that I had in mind, I would like to mention one important topological application of what we are doing. So this is an aside, a topological application. So you all know what, if you have M, basically any topological space, but we can just assume, say, that's a much more general varieties than manifolds, say simplicial manifold, simplicial complex. Of course, every manifold can be put in a simplicial complex. So then you can associate to the Euler characteristic, right, which is just the sum over I going from 0 to wherever the dimension of M of minus 1 to the I to the number of I simplices that you have, right, in your thing. For example, I don't know, if you take just simply a triangle, right? So then chi of a triangle is equal to, so the number of 0 simplices is 3, the number of 1 simplices is 3, and the number of 2 simplices is 1. So this is 1. So the Euler characteristic with the triangle is 1. Okay? So that was this thing. So this is a topological, it turns out that it's a topological invariant, homotopy invariant actually, invariant. And why it concerns us, so now one can express it using cohomology groups. So this is actually the same thing if I write the same sum but with cohomology groups. So sum 0 to the dimension of M of minus 1 to the I to the dimension or a rank of H, the ith ordinary cohomology. So this is just not coherent cohomology of bundles that we're looking at, but just ordinary cohomology of the manifold. So this you've seen, I'm sure, in many of your courses. And well, there is, maybe I'll just mention the Hopf index theorem. Which says the following, that suppose now you have an oriented manifold, and let's gamma so now it's a section of the tangent bundle, which is a section of the tangent bundle called a vector field on the manifold. Then it's some localization principle to which we'll come back. Then the Euler characteristic of M is just the sum with some multiplicities here, which I'm not going to define precisely, but these are some integers for the zeros of the vector field. So for example, you know, if you have the sphere, and then you try to comb the sphere, then you have the two, the north and the south pole, where you know, you do this horizontal rotational field, then there will be 2 points where the field is 0, you know, the north and the south pole. And so that will say that the Euler characteristic of the sphere is 2, and it's true if you verify this thing. It is 2 really, so it does work. These indices are somewhat irrelevant for us now. These are some integers you associate the local behavior. So determined by the local behavior of gamma. But this will not be so important for us. But it's clear why this is important for us now, you see. It's not so surprising. So I'll just want to define a formula. I'm jumping through some things here, but I assume that you know what the Euler characteristic is, and then this form is very nice. The actual proof of this thing is a little more involved, but it's not so. I don't want to do it. I just want to give you the formula. But so you see what's going on here, why this is important for us, because what we're looking at is the zeros of the tangent bundle. And of course, we know what the zeros of the tangent bundle, or any bundle, are. They're given by the number of zeros, or the cycle of zeros is given by the Chern class, the top Chern class of the tangent one. So recall that in our language, if we had some variety x, smooth variety, and we had a vector bundle, then gamma is a section of this vector bundle, then in fact the cycle, as long as gamma is non-degenerate in the algebraic sense, then the cycle, this cycle in X, its class in the Chow group, okay, I'm just, so sorry, now I'm going too fast. So the Chow group of X, we can take this, the zeroth of the, wherever zero, the vector, the section is zero, that defines a cycle in X, so it gives an element of the Chow group of X, and what the definition basically is, as long as with some very mild conditions on gamma, that this should be simply, what should it be? The top Chern class of V, so C, and here you have the rank of V, so the top possible Chern class of V. Okay, this is this. So you see it's very close. And of course, here the top Chern class is precisely the top for the tangent bundle is precisely the dimension of the manifold. So the top Chern class will have the same dimension as the manifold. So actually it will just mean being C0 or A0, so it will just number of points. So the formula, and this is true now, which I'm not proving, is that in fact in this situation, X smooth then what we have is that well, let's assume it's projective. I'm not sure, I don't think it's necessary, but anyway, just to be sure, then the Euler characteristic of X is equal to this, so let's just say dimension is n, so that I have an easier way of writing it down, is just Cn of the tangent bundle of X. So n is the dimension of X. Okay? And I vaguely proved it. I mean, I didn't really prove it, but you know, you see it's very close. If you combine it with Hopf-Index theorem, then this is true. And this is really great. I mean, actually, if you think about it, it's already pretty fantastic that it's kind of, we are cannibalizing a little bit of our calculations, because you see, remember, I started with some space, then I defined these Chow groups, and the Chow groups, then I defined intersection theory. And these Chow groups are actually kind of difficult to calculate, but in this affine stratification case, they were not so difficult to calculate. Okay, so we calculate all that. And I mentioned that in the case, in this where we are with this Grassmannian, so in this affine stratification case, actually this HIM is the same as the Chow groups, right? So because if you have an affine stratification, then and these things are the same. So actually, I could replace it. So maybe I write this down. If we have an affine, there is an affine stratification, then in fact it's true that H2i, so AI is equal to H2i of well, they're canonically isomorphic, and the odd cohomology is 0. Okay, so like for the projective space, you know, the cohomology projective space, it's exactly that thing. So whatever this cannibalizing, what I'm saying is the following. So you see, what's happening now is that, say, I take projective space or Grassmannian or some space like that, or any other space actually. What you see is that the Euler characteristic is some, well, here since all the i's are even, so it's just going to be the sum of the dimensions of the cohomologies, or sums of the dimensions of the Chow groups. Okay? And the dimensions of the Chow group, this sum, is actually expressed as an intersection number, as a Chern degree of a Chern class of the tangent bundle of the space. So somehow we defined a ring, and a certain number in this ring is actually the dimension of this ring. That's what's happened, right? It's clear what I said? The dimension of the ring is this A dot, and then, so that's, I think, is pretty cool. So you can check this in some exercise for P and for the Grassmannian. The calculation is not so easy. So this is not so difficult to calculate. We just use the tautological sequence, or for hypersurfaces, the adjoint junction formula, sorry. Sometimes these are not so difficult to calculate. So for Grassmannian, we have this formula. If I want to calculate this and do calculation, T of Grassmannian is just Hom SQ, where those S and Q are the tautological sequence elements. Okay, so you will be able to use that. And then for hypersurfaces or complete intersections, you can use the normal bundle. For example, for a hypersurface, of degree D, you can use something like, so that's X, then you have a sequence over that Tx, T, well, if it's in projective space, some Tpn, and here you have the normal bundle, but the normal bundle is precisely going to be of D or something like that. So using this sequence, you'll be able to express the Chern classes of Tx, and you can make the calculation that you want, you know, this calculation. Okay? So these techniques then allow you to calculate this, and so that allows you to calculate the Euler characteristic finally of these varieties. By the way, it's going to be pretty incredible sometimes because, of course, here in this affine stratification case, sort of it's a little, well, doesn't look so interesting. All the signs are positive, and it's just sums of dimensions. But when you start doing hypersurfaces, then very easily you might develop odd cohomologies. So for a hypersurface, it's not going to be true anymore that this is not true anymore. You don't have affine stratifications. So there, you'll get some numbers that will see the odd part of the cohomology that's not seen by the Chow group, but this intersection number that we are calculating, this will see that. Okay, so this will remain true. So you'll get some very non-trivial data about the varieties. Okay, so that's all I wanted to say about that. So let's go now to our next story, which is a little more difficult. So this was just a little remark, but it's some use of what of the calculus we've developed. Okay. So now let's do lines on varieties or lines on hypersurfaces, okay? Now let's say hypersurfaces or something like that, or just varieties. Or more generally, linear subspaces on subvarieties generally. Okay, so what do I mean by this? So this is now more difficult, but also very old. I mean, it's 19th century. enumerative questions. So far, what are we able to do? So we solved questions like I did today. We have I did a simple one, but you can do more complicated ones. 4 lines in space, and you calculate the number of lines intersecting all 4 lines. And we did that by intersecting concrete cycles. So this was easy. But very often, sort of classical problems are when you're trying to understand the number of extended objects on a variety. So for example, you take a cubic hypersurface in P3. So a basic question. You take, say, a generic cubic hypersurface in, say, P3. So you simply write down an equation, right? That's what it means in 4 variables, homogeneous equation of 4 variables. And so it looks like this, f equals 0, where f is some homogeneous degree 3 polynomial in 4 variables. And the question is, describe what can you say about the lines. So that means one-dimensional linear things that are actually it will turn out to be there's a finite number of them, we can count them, and that's what I'm going to be explaining, okay? So you see, it's a little different from what because so far we were kind of counting points, or we reduced everything to points. And now we are trying to understand what extended objects, which are more complicated. And these things is pretty modern. I mean, questions like this are, it's very, not this one, but slightly more complicated ones are a matter of sort of current research. So these are now much more difficult questions. But this one we'll be able to solve. So I'll explain now. There's a basic technique to do that. And it's actually some generalization of a Grassmannian that I'm going to introduce that will help us, which then also will lead us to an even bigger generalization of Grassmannian that's called the Hilbert scheme, which is where I'm trying to go, from which then we can construct all sorts of moduli spaces and much more complicated objects. But so this is sort of a first step. So to do that, we introduce a variety which will help us to count this thing. Because a priori it looks hopeless in a sense, right? I mean, how do you describe, you just write down an equation, how do you describe lines in them? And that just seems very hard to understand. So we have to reduce it to our calculus, and reduction means we introduce a new space. So the space is, I just first do the stupid thing. That, of course, doesn't help, but let's just do that first. So I'm not going to do lines. I'm going to do, say, k-dimensional subspaces for now, just some very general thing. So so I will keep this, so we can look at higher codimensional subvarieties, but for today, I'll only look at hypersurfaces, so that means one equation, okay, for simplicity, although that's not necessary. So this I'll keep, but I'll start with, instead of lines, just some general k-dimensional subspaces on a hypersurface, okay? So we start here. So again, so X is some hypersurface, hypersurface, and K is just some integer, right, as usual. And I'm interested in this thing. So let's, fkx like this. And this is just, so hypersurface in Pn, as always. So it's lambda, Yeah, this is my eternal thing. So I'm just going to identify those things. You remember, there are lines in projective space, and there are linear spaces in the above affine space, and there's always a dimension difference. And I'll denote, so these lambdas before were subspaces, now they're lines. It's the same thing. So if you like, So K plus 1, so this corresponds to lines in the hypersurface, and then so the projectivization, so I continue the condition, if I projectivize lambda, then this will be in X, right? That's the correct condition, right? So I mean, this is a shift because linear spaces in affine space are the same thing of rank k plus 1 are the same thing as k dimensional, sort of what we call linear subspaces in Pn. And I want that the projectivization of this linear subspace should be in this X. Okay? So this is what I'm trying to describe. When I write this question mark, it's more precisely I'm trying to describe this set. So at the moment it's only a set. So the first step, I'm going to describe this as an algebraic variety also. So let's do that. And for that there is this is actually it's pretty complicated. I mean, it's clearly cannot be something very, very simple. So because let's just look at a simple example of how complicated it is. No matter what these parameters are, there's a very easy way of giving an example of this. For example, let's f to be just x, say 1 to the power d, right? So let's look, that's a degree d homogeneous polynomial, so that's the 0. Of course, it's a very ugly, but still it's a d-fold hyperplane in projective space. So if you do that, it's easy to describe all the k-dimensional subspaces. It's just going to be, so then in this case, fkx is just the Grassmannian of k-planes in an n-dimensional subvariety, right? So instead of an plus 1, it's an because x1 equals 0 now. Right, so we can describe what it is, but it's pretty huge. I mean, obviously, this is already kind of bad in the following sense that it's intuitive. It's rather clear that if I set up the parameters right, then there are not going to be any subspaces of a certain dimension. But there will be for a generic hypersurface. But I cannot, even for the generic hypersurface, there are no k subspaces. For this particular one, there will be k subspaces. So it already shows the complexity of this thing. It's not going to be very easy. And so it's all the more surprising that it is very easy. So let me explain the trick. And this trick is basically sort of similar to what we did the Grassmannian and the tautological bundle, which is that instead of doing it for a single variety, this fkx, we're going to do it for all of the varieties together. And that thing, it turns out to be much, much simpler. Okay, so let's introduce this variety phi, k and d, say, something like that. So this is the universal phi, this is called the Fano variety. That's why it's f. So this is Fano variety. And now this is the universal Fano variety. And we are going to do the following. I'm just going to put the whole thing together. So how am I going to do that? I'm just going to take the space of all hypersurfaces. They're easy to describe because they're just given by a single polynomial. And then for each of them, I'm just going to put the, okay, so it's just going to consist of pairs of f and lambda such that, so this is going to be so this f is in some projective space of capital N dimensional projective space, which is the space of all, so I'll write that down later. So there's a space of all degree d polynomials. So maybe n sub d, well, anyway, it doesn't matter. I'll just call it n, not to obscure the notation. And cross, and now I just look at the Grassmannian. So I look at all possible planes, right? So just the Grassmannian of k plus 1, n plus 1, like that, right? So it's all possible planes. And then I just write down our usual incidence variety. It's just the same thing as so the same condition. The condition is that p lambda is in F0. Okay, well, I'll just do that. Okay, and so this is this pairs, so it's a subset of this product. Okay, so I have a product of projective space, Grassmannian, a beautiful smooth variety, and I have a single condition which is the same. So I just put everything together. Okay, you don't. So the fantastic thing here is that this allows me to look at this thing which looks awfully complicated if I fix f in the opposite way. And this is a very, very general trick which will help us in the other direction. So now I have, if you like, two projections. I have phi, k, n, d. So I can map it onto Pn. So let me explain this n thing here. So n is just the set of, is the space of all degree d polynomials. So this is the dimension of degree d polynomials in how many? N plus 1 variables. Minus 1, because I projectivize it. Okay? And so there's a formula for that. So that's just n plus d, choose d or something like that, or n, doesn't matter. Okay, so that if you take n plus 1 variable, choose n minus 1. Okay? So that's what this n is. That's just each point here represents a degree d polynomial. Okay? Okay, so going back here, so one is this Pn and the other is the Grassmannian, right? And so what I was saying, so far I haven't done anything in this sense, because what I was saying is that if I fix a point here, so if I take an f here, then this is going to be pi 1, so this is pi 2, then pi 1 f, pi 1 inverse f, so the pullback of f is equal to just fkx. Well, x is always f equals 0, okay? Or let's call it xf maybe, and it's not so confusing. Okay, so this f equals 0 I call xf also. So, okay, so this is a tautology, but already it's not quite a tautology. Why? Is because now it's actually, I'm completely in a algebraic situation. It's easy to see, it's an algebraic now this is an algebraic subvariety given by some equations. I'll explain it in a second. But it's intuitive, it's relatively clear now that these are just equations. As I said, I'll explain more precisely in a second. And so if we know that, then the pullback of this thing is going to have an algebraic structure here. So, and so what that, yeah. So this already puts things in our framework. But what is really exciting is that the thing is that we can now study what is happening in the opposite direction. What happens if I fix a line? What happens if I fix a lambda in the Grassmannian? And what is pi 2 inverse of the of this thing? So if I fix a k-dimensional subspace, remember, of this n mod plus 1 dimensional variety, take the inverse. So what does it mean that a p lambda is f0? Now I'm going to reformulate this in the following fashion. So remember that, so what I'm trying to say is that what is p lambda is in f, in xf. This is the same thing as saying that f is 0 on lambda. So f restricted to lambda on that linear subspace is 0. Right? So again, to say that a line is in a 0, so it's difficult to find all lines which are zeros of a set, but the other way around is very easy. If I fix a line or a subspace and I want to know what are the polynomials which vanish on that line, I just have to restrict the polynomial on that fixed line, and that is just a linear condition on the coefficients of this polynomial. It's kind of obvious if you think about it. You just take any polynomial, say x1 squared plus, so this is something, just I write down some very short, ax1 squared plus b x1 x2 plus c x2 squared. And I take a simple condition, say a simple line, say that x1 is 0, so the line, now lambda, is x1 equals 0, right? So then if you restrict that, then it just means that you set this and this 0, and this just will mean that c equals 0. 0, and this c now is in this Pn. It's like one of the Pn collects the coefficient, P capital N, collects are the coefficients of the generic degree d polynomial, and it's just a linear condition now on the coefficients. Okay, is this clear? Yeah. So this is a linear space. This is just a projective space. It's just a projective space. Subspace of codimension. So what is the codimension? So the codimension is actually the following, is that when I restrict this thing, then what do I get? I just get a degree d polynomial on a k plus 1 dimensional space, right? So now what is this thing? Is a degree d homogeneous polynomial on a k plus 1 dimensional space, right? That's what happens when you restrict it. And the condition that this should be 0, okay? So it's, again, it's cannibalizing our idea, so I have to, how many conditions is that, right? So it's as many as as many polynomials we have, right, of degree, now not on an n-dimensional space, but on a k-dimensional space. So the codimension, so continuing this codimension here, of this projective space is, so how am I doing the time here? I think I spent too much time. Yeah. 56. Okay. Is precisely the dimension of this possible space of all polynomials, of a space of degree d polynomials on a k plus 1, which is just k plus d choose d. Okay. And so actually it's easy to see. So you see in one direction this thing is very complicated, but the other is very simple. For each point here, you just have a projective space. It's just a projective vibration. So actually the theorem is, which I'm not going to prove, so I have to finish here. I'm a little bit short of actually doing this. I'm almost there. I'm going to write down the formula for you, and then you'll see it's. So the theorem is that this phi Pn, this was a bit too much for one lecture, is a codimension k plus d choose d smooth subvariety. So I didn't prove this, but it's almost kind of intuitively not so surprising when you have simply a projective bundle, a bundle of projective spaces on a Grassmannian. So it's not surprising that it's smooth, and actually it follows from that, right? So even though this F thing is very complicated, the fibers of this map here, the universal thing is actually smooth. And of course, that makes things very easy to calculate. And in fact, I am going to use this in a way to describe what's happening, and this is the following. So I have to stop now. Moreover, so we have the following construction now. Or just representation of this fkx, xf, which is the following. So what we can do is I can take the Grassmannian, so I can just take up this idea and reverse it, sort of cannibalizing it much more. And if you think about it, it's just a tautology of what I'm going to say. But it's just the following. I can just take this Grassmannian, and now this has a universal bundle. This universal bundle is literally this lambda, right? So this is this universal bundle that we always use. And just let me check the time. Well, pardon? Yeah, sorry, or tautological. It's also called universal. Yeah. So it's this thing that I used before, right? So this. Whatever, Q. So I have this situation. So I'll just finish with this. So now what I can do is the following. Suppose I have F, right? So because I want to understand this. So then that thing that I was saying there about restricting F to lambda being equal to 0 can be translated in the following way. I'm trying to find this fkxf, which is, of course, is a subset here, right? It's a certain set of subplanes. So I want to describe this. And the way you do that is that, of course, this restriction precisely does the following. I'm going to look at the d-symmetric product of S dual. So that's precisely, what is that? That's just symmetric, homogeneous degree D polynomials on S. That's what this is, right? So if you take symmetric tensor product of, so this is just homogeneous degree D polynomials on S. That's just some tensor power S star. And I look at that as a bundle over the Grassmannian. And of course, I have a global polynomial of degree D on the whole space. I just defined gamma F here, a section of this bundle, which simply gamma F at the point lambda is simply F restricted on lambda. This is our usual tautological trick that we've actually used many times. And what I want is that it be 0. Okay? So actually F, so this is, sorry, I just took 2 extra minutes, but I'm really finished. So I'm not going to be able to do the calculation, but at least I write the formula. So actually F is simply equal to wherever this gamma F is equal to 0. Right? Because when I restrict F, 0, those are these planes. And so now this is exactly our Chern class situation. So the final formula is this. So then if I want to calculate the class of fkxf, then I just take C at that dimension, k plus D, choose D, Chern class of this bundle sim D S star. Okay, so this is a little, looks complex, but still it's simply a Chern class that we can calculate. And we can do it, not so difficult. And for example, we get that for the original question, you get 27 lines. But I didn't have time to do that. I'll do it next time. All right.